So, welcome. We're going to spend the next 60 minutes kind of jumping around some random topics. In my role, I travel around the world a lot talking to customers ranging from early adoption startups who are just getting started, some of the big unicorns, mid-market customers, big, large enterprises, global organizations, governments, non-for-profits. And so that allows me to see a lot of kind of patterns of behavior, patterns of adoption, what works well, what doesn't work well sometimes. And so I just want to kind of share a bit of these insights with you and see what's kind of changing, particularly this week when there's been a lot of announcements coming out. This is a good URL if you haven't seen it already. If you want to see all of the announcements from reInvent, links to some of the articles, white papers, blog posts, product pages, customer testimonials. It's a great place just to kind of go and start looking for information you can filter through by different services as you see fit. All right, so let's talk about architecture. I'm from Australia, so you're going to have to forgive any references back to my little homeland there. But when you think about architecture, this is the architecture track. That's the leadership session for it. A lot of people kind of get mixed up between architecture and engineering. If you think about architecture, architecture is really about design. It's about the creative process of listening to what are your customers' requirements. When I say your customers, it can be the end users, it can be the business, it could be other technical teams that you're building systems for. And one of the most important things you have to do as an architect is to start by having a really strong vision. This vision of what is it that you want to design, and what are the attributes or the guiding principles that you're going to use to define the architectural vision that you have. If you get it right, as an architect, it provides a very strong sense of purpose for everybody else that's going to have to build to that architectural vision that you have, to the users that are going to have to use the systems that have ultimately been built, and at some point in the future, those that have to turn it off and migrate it to something new. I actually would argue that as an architect, one of the things you should always think of when designing a new system, and before anyone writes that first line of code, is how am I going to turn this off in the future? Have I got the right interfaces and abstraction points that allow me to put proxy in place and direct customers and traffics away from this service onto whatever the replacement is going to be? So having this strong sense of purpose. If you have that really strong sense of purpose, which actually often is kind of this clarity of thought, it inspires others to push the boundaries of what's possible. Why do we want to learn a new technology? Why do we want to learn a new architectural pattern? It inspires them. If you don't have that bold vision, they're probably just going to build exactly what they've built again and again and again. This is actually one of the reasons why innovation can be hard to do in technology teams, because they kind of fall into this trap of just repeating the same thing. If you have that sense of purpose, you inspire others to push, you start working more in the art of the possible and not in what's probable. And the difference between possibilities and probable is going to happen whether you like it or not. It's kind of like, very evolutionary, slightly faster, maybe slightly more efficient, slightly cheaper. It's just like the next little point version upgrade of something. Possible, is we think it's possible, might not have done it yet, we're going to prove whether it is or not. And that's really where the breakthroughs come through, is when you shift from working in the world of probability into the world of possibility. When you start getting into the world of possibility, though, there is going to be failure. It's okay. I would argue, and I talk to technical leaders all the time, I love to ask them, particularly when there's a CXO conference, there's 20 people sitting around a room, and I'll ask them, hands up if you failed at something this year. And they all look at each other, and no one will put their hand up. And they all kind of smile and think, yeah, that's good, we're doing a good job. The reality is, if you're not failing, you're not trying hard enough. You should be pushing the boundaries of what's possible, find where that edge is, and then you back off a little bit. Back off, and that's where you want to be. Through failure, you learn a lot as you go through this. As an architect, as you do this, you want to be really stubborn on that vision. Once you have that vision and you've kind of verified it and ratified it, and you do that by talking and sharing with other people, and you get feedback and you kind of go, look, I think the people I trust are telling me this vision is good. Stick to it. Because you are going to potentially have some of those failures along the way, people are going to tell you constantly, it's not going to work. It's impossible. I tried that and it didn't work. Stick to the vision. The vision is right, just the implementation is wrong. So be flexible on the details as you go through. You're going to learn as you go through things. Actually, over projects that actually go for a while, the technology itself is going to change. You just think about how many design decisions you would have made last week, which would be vastly different this week based on announcements in just 1 week. This happens all the time as we go through. Now, if you get this right, one of the things that starts to happen is when I work with technical teams, I started noticing this pattern of behavior. It's actually a cultural pattern within organizations, which is, as technologists, when we get hit with change, some teams really struggle with being innovative. Actually, it's not just teams, some companies. They'll talk the talk. We want to be highly innovative. We want to disrupt, and nothing happens. And what actually happens when I go into those organizations and sit with the teams is I find that in the meetings, all of their conversation is all focusing on what they're going to lose. We've had this system for 10 years. We know how it works. We have skills, we have experience, we have process. It works, it's stable. I don't want to lose that. I might lose my role in the team. I'm the subject matter expert for this. I will not be the subject matter expert if you change the technology. You hear this language a lot. I'd hate to tell you, but your companies, unless you're really in kind of maybe risk, they're not really paying you to come up with reasons not to do things. They're paying you to be creative and work out where are the risks and gaps and then how you're going to get around them. When I compare that and contrast it to teams that are highly innovative, what tends to happen is it kind of flicks around a little bit, and these teams are focusing on what they're going to gain. Now, you've got to be careful. I'm not saying to ignore what you're going to lose, because you have to be aware of it and you have to have plans for it. But you want to spend more time focusing on what you're going to gain than what you're going to lose as you go through. Now, those of you in the room who are in leadership positions, you are the best person to actually shift this around. If you're in a meeting and you hear that language where everyone for the last 30 minutes has just been coming up with every reason why you can't do this, time out. Stop and actually be really clear and say, hey, for the next 15 or 20 minutes, I want us just to talk about what the opportunities are going to be, what the positive things are going to be. I don't want to hear the reasons we can't do. You'd be surprised just by doing that and making that conscious decision to shift that conversation. It'll be really awkward, to be honest with you, for the first 5 minutes. There might be deathly silence in the room. But eventually someone will start. And once they start, the others will start jumping in on top of that. And before you know it, you've shifted that entire focus and the context of how people are looking at change pretty quickly. All right, let's talk about predictability. When I think about architecture, and one of the goals when I design systems within AWS and with customers, the one thing I'm really actually trying to achieve is that that system has to be predictable in how it behaves under any scenario. How is it going to behave when it's working well? It's pretty easy. Hopefully it's doing what it's meant to do. How is it going to behave if it becomes overloaded? How is it going to behave if it becomes, if something fails in it? There's an error that occurs. And by thinking through each one of those scenarios, if I can't predict how the system is going to behave, I don't have a good architecture. This sometimes means the simplest way to actually make a system predictable is that one of the hardest things to design around is partial failure. It's kind of thinking there's 3 possible states for a service often. It's fully working, it's completely broken. Both of those are easy to deal with. How many of you dealt with a system that's failing 5-10% of the time, and you spend a lot of time troubleshooting it, trying to work out what's happening, hours and hours. Meanwhile, everything else around that system is also having partial failure. And your customers using those services that are in partial failure have a bad time. So one of the ways to drive predictability is that if something is having partial failure, sometimes just to deliberately shift it and push it to complete failure. Just fail it, because if you've designed it well, other systems will just route around it. They'll go into queue mode, for example, and the system becomes predictable. because you designed for that as you go through. It's one of the key things that when I work with our architects, is asking them around what are the scenarios they thought of and what would happen if this happens. What happens if the buffers become full? What happens if the queuing overloads and you can't clear it fast enough? They're the questions you want to ask. This is important. You actually heard Dr. Werner Vogels this morning talking about this in his keynote, which is everything fails all the time. It's true. I'm going to come back to this in a couple of slides' time about why this statement's becoming more true as we go forward, which is kind of an interesting thing. If everything fails all the time, again, you want to reduce the blast radius of adverse events. You can do that, again, by making sure that the design from the get-go has that thinking into it, and that you define where those boundaries are going to be, and when it's triggered that it's not working, the other systems will continue to work around it. It's this collaboration as things go through. So that's a bit of scene setting around architecture. Let's talk about workloads of tomorrow. So if you think about the announcements this week, I've kind of been thinking about them as 4 different types of themes that have come through. One of them is that there's a lot of announcements, technologies that are going to help us run future workloads that just haven't been possible today at scales that are just, kind of very edge use cases at the moment are going to become more common. Second area is around simplifying technology. Those of you that are in operations, for example, how do I manage these large environments smarter and more efficiently? We've got smarter security coming through. We're actually seeing AI and ML coming into security services where they're able to give you proactive advice and guidance as to what the causes may be. And then last but not least, edge-to-edge connectivity. That's kind of the 4 big themes as I think about the hundreds of announcements that have come out in the lead up to reInvent and this week itself. So if you think about these future workloads, these are the attributes that are fairly common. They're not going to be a big surprise to you. First one is that if you think about workloads, they're going to be made up of many services. The aggregate is going to be massive, right? But each of the individual services are much smaller. That's what you want to be doing. You want to have lots of little microservices, quite simple. But when you build collections of services over the top of them, they can do amazing things. This means they're going to be highly integrated and intermeshed. You've got lots of different pathways of data and traffic, messages, etc., passing between these systems as they go through. As a result of that, I want to have really tight security controls at every layer. Actually, this is quite fluid, and it's changing all the time, because I don't know what other developer teams might be doing with their services as they go through. And so if I'm relying on their security posture, it's a weak design point. I want to make sure that my services that I'm building and I'm designing have that security built into it. Actually, security, we always say security is number 1 priority at Amazon. And as a result of that, before you even kind of write that first line of code, think about security and put the foundations in place. Again and again, I see teams who do rapid prototyping, and they will add security later. I can tell you now, once you write something, if you haven't written it from a good posture of security, trying to wrap it around it afterwards is never as good as just doing it from the start. I actually talk to teams all the time where I kind of have this methodology. So I'd rather you start slow, get the foundations right, and finish fast, than start fast and never finish. Right? Where you take something that's prototyping, it's really good. You proved the hypothesis of what you're trying to do, but now you've got to kind of productionize it, and because you didn't think about it, it just becomes almost impossible. By the way, the business has been really excited because you proved something for them. They just want to deploy it straight through to production. Happens all the time. You're going to have many more individual services. We see organizations running hundreds, thousands, big globals, tens of thousands of individual services within their organizations. But each of these services, simpler functionality, but each one of them, actually, if you look at, as we go more towards a digital future and the power of data, the performance and throughput for each of these services is shooting up as it goes through. This is why Werner's comments about everything fails all the time is really relevant, because you've got more components. If you think about classic availability engineering practices, the more things you have, the higher the likelihood of one of them failing is. And this is why you need to really design it in to think about asynchronous communications between things. So if one of those services fails, it's not the end of the world. Actually, customers probably won't even notice, even though it might be a bit of a delay. Maybe we didn't put that new registered user straight into the billing system. It's okay. They're not going to get a bill for another 30 days. Doesn't matter. Compared to those old monolithic systems, which was part of the registration process, if inserting that user into the billing system failed, the registration failed. Happens all the time as you go through this. Last but not least is the amount of data that's being generated, collected, and processed. Is it continuing to increase at an incredible rate? It's accelerating. I don't think we're really even seeing the true start of the scale of data. Because I think about all of the devices, some of the sensors that are coming through this with sensor fusion in the world of connected devices, and what AI/ML is going to allow us to do, robotics, etc. Starts almost feeling like you're working in a science fiction movie when you start looking at some of this technology. It's going to drive data volumes that we haven't even seen yet as it goes through. There's new architectural patterns that come through as well. Again, we talked about security being integrated at every level. One of the things I'd like you to think about is I want you to think about designing for hyperscale from the get-go. Now, this doesn't mean I want you to over-engineer from the start. What this means is you should be thinking about, I am building the service at the first point to only deal with up to 100 transactions a second. And I know what's going to happen, because again, we're aiming for predictability here, where the choke point is going to be at 100. And I have ideas how I'm going to get from 100 to maybe 1,000, order of magnitude increase to 1,000 transactions per second, to 10,000, to 100,000, to 1 million plus. Classic mistake I see is people over-engineer and they build for the 1 million plus transactions and they're really doing one a day. That's over-engineering from the get-go. But you should be very cognizant about where those choke points are going to be and how you're going to implement those scaling activities within the services that you're building and designing from the get-go. You want to have really strong emphasis as architects on the service boundaries. What I mean by service boundaries is where does that service start and stop? What is its responsibility? And what is the responsibility of the other services that it has to work with? Is it responsible for dealing with failure? Or is the other service going to be responsible for it in terms of queuing and caching things? This gets quite complicated when you start thinking that you could have serialized lines that a transaction has to go through. It could go through 10, 12, 15 different microservices in a serial fashion. And this is where services like step functions actually really comes in and makes a big difference. You want to design for optimization from the start. Again, don't spend too much time doing what we call premature optimization. We see developers particularly are really excited to find that perfect algorithm at the get-go. It doesn't matter. It doesn't matter if you're running 100 transactions per second. It matters when you start getting up into tens of thousands and above. That's where you can start optimizing. By the way, when you're optimizing at that latter point, you have more data telling you where the hotspots are. This is where things like Code Guru and X-Ray really come into play, is they give you signals where those slow spots are as they come through. Another fascinating area here is that the lifespan of these services is actually pretty short. If you think about some of the systems that have been running in the past, we wouldn't touch them for 6 months, 12 months, sometimes years. When I first entered the industry, we used to actually have a competition of which system had the highest uptime. Some of them would be 365 plus days long. And we were proud of that. You compare that to where we are now, and it's actually about how quickly can I bring features and changes to it. Actually, it's maybe sometimes quicker just to rewrite that entire service. Or the transactional load is required, I'm going to shift it to a different technology stack as I go through. Or there's more optimal and efficient ways that I can take dramatic amounts of cost out by flicking across. So things like version control of your designs becomes really key. We see increasing use of smart container platforms. It's a really nice way to package things up. If you do this right, you have continuous removal of technical debt. I think technical debt, it's an overloaded term sometimes. my definition of technical debt is it's not old systems. I can tell you now, I've been to startups that are months old. They have services that are weeks old. And they have incredible technical debt. Because the definition of technical debt, I think, is it's technical decisions that hold you back from future innovation. There are plenty of old systems that are actually architected incredibly well, have good APIs around them, greatly defined service boundaries. They're not holding an organization back from innovating. That's not technical debt. Doesn't matter if it's a 10-year-old system. If it's not holding you back from what you want to do in the future, it's good. If you write a brand new whiz-bang container-based microservices with serverless and all the buzzwords in the world, if you get the design wrong, it's significant technical debt. You want to remove data silos from storage devices. Again, this volume and increase of data is causing situations where so much data, it really doesn't fit into any system anymore. Actually, I lie. There's only really one system that does store it. That's S3. But it's too big to fit in any other type of database service. And so you're starting to see isolation of data. I've got some within RDS, might have some in Redshift, I might have some in third-party database services, I might have some on-premise, I've got a lot of it in S3, and I have to deal with it in separate ways. Actually, this adds complexity of layers where ETL, for example, extract, transform, and load, you start doing all types of crazy things over the top of that to start managing it. I'm a big believer that the announcements this week around, for example, like Redshift, Aqua, for example, which is really powerful, allows you to do direct queries of that data as it's sitting in the storage system. This unlocks the information that's within those data sets. And that unlocking the information drives innovation. It allows organizations to ask questions, understand what is happening in their business, understand what their consumers, their customers are doing with their services, and actually drives innovation. You want to unlock the power of these data sets. The other thing that I think a lot about is you want to leverage the right compute style. It's no surprise, year after year at re:Invent, there's always a lot of new processing technology added to the equation. And this actually gives you more choice that can lead to complexity. There's more choice than ever for you. One of the things I'd say is, naturally we tend to focus on optimizing workloads when they're big systems. Right? It's easy to understand that if I have 10,000 instances running for a workload, I should optimize that. I can tell you when I do cost analysis studies for our customers, often what happens is they're ignoring the long tail of the cost of compute within their organization. You're running many services, applications on ones and twos of VMs and instances. It's just as important to right-size those ones and twos because in aggregate, they add up really quickly. So you want to be covering both spectrums. If you do this right, you can get cost efficiencies of over 250% plus just by matching that right compute style to the workload. And again, you've got choices now between serverless, bare metal, general compute, specialized compute instances. We also have new technologies where we should be thinking about CPU versus GPU versus FPGA technology, and even quantum computing starting to come into play. Different workloads behave very differently on those compute platforms as they go through. Am I using the right one? One of the big announcements this week I really like is Graviton 2. And the reason why I like Graviton 2, let's have a look at it. This is a kind of jump into some of the stats. This is Graviton 2 instance against a comparable M5 instance type, which is kind of the general purpose compute. Let's get some of the fun stats out of the way first. 44% faster for integer workloads, 24% faster for floating point arithmetic. If you're running your software in any type of kind of JVM, it's about 40% faster. If you're doing web transactions, 24% more requests per second. If you're doing video encoding, 20% faster for X264. If you're doing text processing, for example, loading lots of unstructured documents within your organization, trying to extract the semantic meaning out of those documents using BERT, for example, 28%. This is really the big one here. Many of you, particularly if you're in enterprises, you're using commercial off-the-shelf software that you're paying software licenses for. And often these software licenses are based on a per core cost. Just by switching to Graviton, the performance per core allows you, in many instances, to halve the licensing costs because you just got greater performance per core coming through. So this is a really easy way where, we think about Graviton. It's more than just raw performance speeds. Think about it in terms of what it can do to licensing costs as well. So if you take this into consideration, you start seeing this new pattern occurring, which is I've got all these new compute styles, different instance families, different technologies that I can use. I see organizations that are really good at driving optimization. They're actually never stop migrating their compute. They're always experimenting with it, trying to look at what is the best bang for buck for their workloads. AWS infrastructure is constantly changing, but so is their workloads in terms of the software designs they use, but as well as the throughput going through them. Don't be static with your designs. Again, this comes back to why I think that workload versioning lifespan is getting shorter and shorter, because if you're constantly migrating this all the time. But what can we do to help you if you're moving things all the time? One of them, reserved instances was a great way to save money, but in some ways, they locked you in. So savings plans, which we announced in November before reInvent, is a way to give greater levels of flexibility while still providing savings. So it gives you another option between pure on-demand, or Spot if you really like using Spot, and reserved instances. This kind of sits in between the two. The other one I really like is AWS Compute Optimizer. So this is a tool that allows you to, it kind of uses AI/ML behind the scenes and looks at the actual usage characteristics of your workloads on the compute infrastructure that's running in AWS. And it will model that and then provide recommendations to you in where you can optimize. It also goes a step further though, because it's not just about optimizing your EC2 usage, it also recommends, are there opportunities for you to use auto-scaling techniques? Can you add and remove capacity based on variability? And this is important because I think for a lot of people who are just still getting started with kind of cloud-native technologies, this idea of dynamic workloads can be quite a scary topic. I mean, where do I set the thresholds? What happens if I get it wrong? How long is it going to start up? These tools make it easier by providing recommendations that allow you to get started and then start tweaking it from there. So Compute Optimizer is a very powerful tool. There's some rules of compute that I think of when from an architectural perspective. First thing is if you think about compute is expensive. It's relatively expensive. And so I want to do expensive things once. So anything that's going to consume vast amounts of processing power, I'll do it once, and then I want to reuse the output of that expensive processing as many times as I possibly can. Yeah, this means caching. I'm always surprised when I do reviews of designs, particularly where there's performance problems. There's no caching happening. I mean, all of us know the importance of caching, but sometimes that caching is not where it really needs to be. And so again, this is where profiling can really come into play and help you understand where are those most heavy lifting of processing and is there an opportunity to cache. You'd be surprised if you make different design considerations about how, for example, information data is used, you can cache it, even if it's only got a cache lifetime of a second. If you're doing 1 million transactions a second, that's 1 million cache hits. Even though it gets refreshed every single second. It makes a big difference as things go through. The other thing to always remember is memory is cheaper and faster than CPU every time. If you want to drive cost efficiency down, leverage the memory as much as you can, the CPU as least as you can, within the constraints of what your requirements are for processing and design. All right, let's talk about quantum computing for a bit. Anyone excited about quantum computing? Yeah, it's going to be fun. It's rapidly evolving. There's been a lot of talk about quantum computing for a couple of decades now, but really the reality is starting to hit. You saw in November we actually made changes to key management service where for transport layer security TLS we introduced 2 new ciphers or handshake protocols that allow you to start testing quantum-proof handshakes. Why? Because we think that quantum computing is not that far away from being able to solve some of the mathematical problems. One of them is linked to encryption keys in symmetric key handshakes, for example. This is important because when you think about quantum computing, there are certain workloads that quantum computing is going to be orders of magnitude faster at. There's actually mathematical problems and optimization algorithms that are impossible to do on classical computing within our lifespans, actually within the lifespan of our sun, and some of them even within the lifespan of the universe. You don't want to wait for that. It's not going to be the panacea, though. It's not going to work for all workloads. The best way to think about how quantum computing is architecturally going to help you is, what problems do I have that have a small number of inputs and a small number of outputs, but infinite variability between the two? That's where quantum computing really comes in. Optimization algorithms, for example, packing problems, route finding, weather, molecular science, for example. These are going to be the hot areas for where quantum computing comes in. One of the challenges with quantum computing is there's no defined solved solution for what the winning solution is going to be. There are lots of different approaches here: quantum dot technology, quantum annealing, ion trap hardware, macro qubits, for example, as things go through. What this means, it's really hard to test for applications of where quantum computing may happen. What this means for you as kind of architects is a couple of things. Doesn't mean you should be jumping into quantum computing right now. No. You should be aware of it. You should be really actually aware of what are the compute problems within your industry that you're operating in, and is quantum computing likely to be something that's going to be disruptive? If so, pay close attention to it. If it's not, sure, you can follow it for interest's sake and just keep an eye as it goes through. I think this is going to, if you think about the progress that's been made with artificial intelligence just over the last 5 years and how quickly that evolved, you're going to see that same pace happen with quantum computing as things go through. One of the things to think about quantum computing, though, is the probability engine. Okay, you have qubits. These qubits, when we measure them, when we observe them, we're actually measuring the probability engine. And so there's a degree of error in it. And actually what happens is we actually have to ask the quantum computer multiple times what the answer is. Because when we don't measure it, it actually has every single possible combination within the qubits that's there. And when we measure it, we're asking for a view of it. And over time, we keep asking it again and again. And that more times we ask, we get that probability down. This is why it's okay for doing things like molecular science or weather forecasting, for example, understanding how the brain works from a neuron mapping perspective. It's okay to have a degree of error there. Core banking system? Probably not. It's got a degree of accuracy. Amazon bracket, super exciting. If you're wondering why we misspelt bracket, it's actually a mathematical term, two things, bras and kets. It's kind of really is common notation for quantum states, if you're wondering where the name came from there. It's really cool. You can actually model all this using classical computing. And this is important because when you think about quantum computing, there's kind of 3 areas that we have to be aware of and solve. There's quantum hardware. There's the quantum code, which will control the quantum computer. And then there's the algorithms and the math models that have to be proven, can they work within the quantum world? So there's 3 things that happen. If you think about classical computing, it took time, for example, when we first introduced 64-bit computing, for example. The hardware is always the first one to come through. And there's a bit of a delay as the control of the operating system would catch up, and then more of a delay as applications have to be rewritten to go through that. So the same model is likely to apply to quantum computing as well. If you want to see what they kind of look at, these are the 3 different ones that we're modeled with. They look much cooler than silicon-based things. This is because you have to do things with qubits where we have to kind of cool them down. They don't like any type of interference, because if you interfere with them, you disrupt the entanglement of the qubits. If you're wondering what a qubit and why it's so important is, if you think about classical computing, and you think about when we moved from 8-bit computing to 16-bit, the machines got more powerful, faster, and could deal with more complex processing. Qubits is pretty similar. If you look at kind of what's best in the industry at the moment, it's roughly around 50 to 70 qubits of complexity. Starts to be able to prove some things. At about 100 qubits, some algorithms will start become possible on quantum computing, such as optimization routines, traveling salesman type problems. When you get to about 300 qubits, which is not that far away, 300 qubits, if you think about at any point when that system is running, it can represent more numbers at once than there are molecules in the entire universe, just at 300 qubits. At 1,000 qubits, things get really interesting. We'll be at 1,000,000 qubits sooner than you realize. And this is really important because if you think about the natural world that we live in, it is actually in a quantum state. Okay? Molecular science, material science requires understanding of quantum effects. Cutting-edge health science and medicine starts touching on quantum effects as well. You can't model the real world perfectly if you can't model quantum effects. And that's where classical computing is really an approximation of the real world. And as you start getting more detailed in it, the error rate in classical computing of the approximation gets way out of control. And this is why quantum computing in different industries is going to be a big game changer. All right, databases. Databases, there's lots of new design challenges that come in, particularly when you start doing serverless and containers. We know some of them, for example, if I have 1,000 parallel Lambda functions, they've all got database connections open back to the database. If I do failover of databases, it's an outage and that can cause some issues when you've got lots and lots of, hundreds, thousands of clients connected to it. We know databases need larger scale. Developers want more choice. Again, as data sets get bigger, the efficiency and optimization of data sets is just as true to picking the right database type for the types of analysis I want to do as it is to compute to the workload. We're seeing AI/ML starting to be integrated directly into the database layer. So can I do forecasting using AI on the data as it's in the database? Can I do fraud detection, bad actor detection, directly with the data as it's in the database itself? We're seeing that people want to have more third-party choice and integration with different tooling. It's all good. RDS proxy, this is probably one of my favorite ones. If you want to have resilient design and go back to that concept of predictability, this is one of the best tools for it. It gives you 66% reduction in failover times. And it's actually really simple to turn on in front of the databases that you already have running in RDS and do this. And it moves a lot of, sometimes some developers push a lot of the complexity of how to deal with failover into that app layer, RDS proxy layer, to remove that and push it back down into a managed service. One of the most important things, just behind predictability is abstraction. And the way to think about abstraction is if I have service A and I have service B, and service A is communicating with service B directly. You think about, the old way we used to write code, might have a socket on the server, loopback, whatever it is, DLL, doesn't matter. They're directly linked. If I change service A, I probably have to recompile service B. If I change the feature set of service A, I probably have to add it to service B. They are intrinsically linked. That's bad from a design perspective. I want to put an abstraction layer between the two so that I can modify service A and I can change whatever I want. As long as I don't change that abstraction definition, I don't need to touch service B or C or D or E that is talking to it. This is why abstraction, and abstraction, API, great abstraction layer, one of the best. Service-oriented architectural design, it's all about abstraction. But where things go wrong sometimes is where as architects, we put too much extra abstraction in. And it really is a balancing act. What's the minimal amount of abstraction that gives me the most flexibility? A common mistake I see in organizations where they get a little too clever sometimes is they have service A, abstraction layer, abstraction layer, abstraction layer, abstraction layer, abstraction layer, service B. Have you ever tried troubleshooting what the hell is happening during an outage when you have that many abstraction layers? It's impossible. I see this mistake really being made a lot in the world of containers. Containers is new. They have many good elements, absolutely. But at the same time, there's a lot of new technologies and there's just a lot of fast-moving things. And I see sometimes there's too much complexity being added in there. And that the savings they thought they were going to get don't materialize because it's got too much abstraction. So any chance you have to simplify the abstraction models within your services design, go for it. It will actually help stabilize the platform as you go through. AI/ML's a lot of change here. One of the things here, just from an architectural point of view, if you think about how we think about AI, there's the 3 stacks. There's the very bottom layer, which is the machine learning engineering model. This is for people who love getting nitty-gritty detail about CPU versus GPU architecture, TensorFlow versus MXNet. It's really good. At the opposite end, at the top, this is for developers who don't want to know anything about AI/ML. I just want to consume AI services where I get the benefits of image recognition, text to speech, for example, speech to text, comprehension, transcribing, translating services. I don't want to know how the model works. And in between is SageMaker. And this is for people who maybe want a little bit of both. I don't want to drop all the way in where I'm having to deal with machine learning frameworks. I've got data scientists, and I'm going to experiment. What we're seeing is SageMaker is really becoming a platform where there's a lot of new technology coming in. This is kind of the purple shading there, just shows where there's been significant new announcements and development here. And so this becomes important. If you think about your AI/ML architectural designs within your own companies, using SageMaker is a nice, safe place where you're going to see continued innovation happening here around driving it and making it easier. For example, things like running experiments and being able to measure it and interact with it. Or monitor things like model drift over time. Again, because your models aren't static, your consumer behavior is going to change over time. How do I know when it's the right time to retrain the model and redeploy it? This is where Model Monitor comes into play. So about security quickly. Again, in Werner's keynote, you heard him talking about enclaves. Nitro is a big part of our infrastructure, but we've had virtual machines for many years now, EC2, VMware, Firecracker for micro VMs, containerization through ECS, EKS, Fargate, for example. You have serverless technologies, and you have enclaves, AWS Nitro system. Why this is really important is really, it'll be coming soon, but if you're in a highly regulated industry, there is so much pressure from the regulators where they're trying to remove as much risk as they can. And one of the challenges, while everyone is actually being very good in the industry around encrypting data, there is a point where on the server, I have to unencrypt that data, process it, and give it back. And if I have a bad actor with admin privileges, there's an opportunity there that they could potentially intercept that data. Whereas enclaves, for example, I can take that encrypted data, pass it to the enclave with the key, it will process it there, and it doesn't matter, even if I have root admin rights on that server, I can't see what's happening. Really important when it comes to regulated workloads in financial services industry, healthcare, life sciences, and many other industries as well. There's patterns around insights. A big fan of the more telemetry data you have, the better you can not only operate a system, but the better you can design it for its future needs as you go through. From a security point of view, AWS Detective, for example, allows you to see root cause of security findings and suspicious activities. And it integrates well with like Guard Duty and Control Tower, for example, as well. There's lots of services here that allow you to work together. CloudTrail Insights. I like this one because, again, it's the default location for a lot of logs and metrics that's coming out of your AWS resources, and there's patterns that it can pick up. For example, are there spikes in resources? Are we seeing inappropriate IAM activity? Or more importantly, are there actually gaps in maintenance activity? We've seen that nobody has maintained this service for quite a period of time. So being able to get reports from this and gain those insights that point you in the right direction to dig deeper and find out what the cause might be, it's going to be a great time saver. Again, particularly as the number of services that we're running is going to go up dramatically. It's going to get actually harder and harder to work out which ones to focus on when you have hundreds and thousands of them out there. This is a big one as well, IAM Access Analyzer. Just continually being able to monitor and analyze permission structure. Those of you that are doing security well, I don't have to tell you, it gets really complex really quickly, managing all the different profiles that you have, the postures and the policies linked to that, and all the variations in between. So IAM Access Analyzer is a great tool to help simplify this as well. All right, let's talk about S3 for a little bit. S3 continues to be the #1 object store when it comes to cloud. It is really a foundational piece of so much. It started off from its humble beginnings as just being a public data store, often for image data and kind of for websites, to now it's being used for data lakes by enterprises. What this means is the enterprise usage pattern is actually vastly different when it comes to S3. They have hundreds, if not thousands, of different applications in their organization with thousands of users trying to access this data in S3. But they want to restrict access to those data sets per app or per user. And in the current model, you kind of really only have it linked down to kind of a bucket policy, maybe objects. Common practice is to actually replicate that set of data multiple times. So I might have different versions of it, maybe with different amounts of information. It might have personal identifiable information stripped out, may have financial information stripped out of it, so that different parts of the organization is. But if you think about that data is getting more and more, it becomes more costly to replicate it. Costing not just money, but time. If you're trying to replicate tens of petabytes of information, unfortunately, it takes a bit of time to copy it around. One of the things that happens here that's one of the announcements this week, which is really kind of important, is the Amazon S3 access points. This is the ability for you to define different contexts to the data you store in S3. This is far bigger than just being useful for data lakes. I actually believe that part of our well-architected initiative, this will become best practice very quickly. For example, you could have an access point for data for read operations and a separate access point just for write. And just by doing that, you've completely split out the context and the policies that you have for those different operations completely, instead of trying to mix them together within the same policy on the one bucket. All right, edge-to-edge connectivity. A lot of the innovations that you see, particularly this week, if you think, those of you who have been coming to reInvent for a while, if you think back to some of the big announcements over the years, when they're announced, they don't sound that big. But a couple of years later, you realize that they are at the core of just about everything we do. Lambda, for example, when it was released, a lot of people were like, function as a code, sure, it might be a good edge case. But it's actually now used by so many services and so many different design patterns, a way of integrating things together. And this week, you're seeing a lot of this coming through as well. This is happening because we're living in a world of connected everything. There's been a lot of hype around IoT, the Internet of Things. I can tell you from what I see with customers, there was the hype, then it kind of dropped off a little bit. It's actually growing massively now. And it's really being grown by consumer use cases as well as industrial use cases, as people realize that if they instrument devices, they get more data that allows them to have insights and make smarter decisions as they go through. You're seeing the rise of robotics evolving incredibly quickly at the moment. Now, when people think about robotics, we often think about, for example, robotic arms that we see from the VW presentation this morning. We think about humanoid-looking robots, or maybe robots that look like dogs running around. Really, the definition of a robot, it's a physical device that can sense the environment around it, think about what those sensors are telling, and then act upon it. That's really kind of the simplest definition of a robot there is. Your dishwasher is a robot. Your washing machine, robot. Your cars are becoming robots. This is why robotics is evolving really quickly. And as this evolves, these connected devices, they're generating incredible amounts of data volume. Actually, a lot of the sensors are vision-based. They're using computer vision. Why? It's no surprise, our most powerful sense is vision. It's the densest source of information there is. And it's becoming so cheap to add vision to devices. And so you think about automated cars, for example, which are going to autonomous vehicles. There's lots of cool technology like LiDAR and ultrasonics, etc. they can use. Well, they just put cameras on it and interpret what the cameras are seeing and let it drive like that, because us humans will be doing it okay with just 2 eyes. As this volume increases, it's not just about the volume of data. It's also the transactional volumes. When you talk to an organization, for example, in the consumer space, and they want to roll out, let's say I'm going to have a product, it's going to be connected, I want to get real-time telemetry off this data, I'm going to have 1 million customers out there. That's 1 million transactions per second right there. Actually, it could be more than that because the devices might not be connected all the time, and when they connect, they're going to do a batch upload, and you could have peaks to tens of millions of transactions per second. So you need to start thinking about how this design goes. It goes to that earlier point I made around the attributes of future workloads, is you have to be thinking about the hyperscale use cases of where these could happen. What are those edge scenarios? Because if you do, that leads to predictability. The other thing that's going to happen is the processing of this data is going to be spread everywhere. It's going to happen on the device itself, or it may not. I'll talk about that in a second. It may happen on the edge of the network, and it may happen centrally. Actually, it may happen in all locations doing different levels of processing and summarization as it goes through. Connectivity continues to be important from customers. It's just we want more forms of connectivity. You want more control of it. And we're seeing more use cases for global workloads, particularly around multicast routing, for example, secured remote sites through site-to-site VPN. So again, a lot of announcements here. I'm not going to go through all the networking ones. But I like this quote from David Brown, our VP of networking for Amazon EC2, which is the network should not slow things down, but rather promote innovation. Have you ever tried doing multicast before? It's actually quite complex having that built in. Ingress routing, this is really important for many industries where, for example, as traffic comes into their VPC, they want to feed that through a third-party device to do security controls, for example. You now have the ability to actually force that through the device. I want to have inter-region peering. Really important if I'm starting to go beyond 5 nines of availability, for example. Accelerated site-to-site VPN. All right, let's talk about latency. We had Verizon in Andy Jassy's keynote. I just want to talk about latency for a second. Actually, when you think about cellular traffic, it actually started back in 1946 with kind of two-way radio, which was kind of for zero generation. 1979 was the first real analog packet-based mobile phone. 2G was 1991, which is where data first came in. 40 kilobits per second maximum. SMS, for example. 3G, 2001, 144 kilobits per second min. Big jump up here. We started to see waves of innovation of what we could do with mobile devices that were always connected. 4G came along in 2009, which offers around 100 megabits per second of capacity. This is where you saw the next wave of innovation occurring. I could start consuming streaming services directly on my mobile device. I could take video and share it with the world. The rise of kind of social media and what you could do with that, for example, was largely driven by advanced connectivity, faster connectivity at the edge. 5G is happening right now, 2019. It's kind of a best way to think about it is 100 megabits plus. It's more complex than that, because 5G is actually an incredibly complex standard. It's actually lots of different definitions around multiple spectrums. Those spectrums actually allow for bandwidth from as low as 25 megabits per second up to 2 gig plus as they go through. And the way to think about spectrum in 5G is that the higher frequency or the faster bandwidth that you're going to get, the shorter the range is of that cell. This is really important to understand with 5G because it's not going to be equal everywhere. If you're in a high-density population area like a city, sure, lots of cell towers, higher frequency. If I'm in a rural situation, I'm trying to use 5G, for example, in a smart agricultural environment, likely I'm going to be using a lower frequency but get more distance out of it. And there's going to be combinations and variations of this as well. Where this really kind of comes in to play is that the latency in 5G drops dramatically. So today in 4G, it takes about 130 milliseconds on average, depending where you are in the world, to get out of the 4G network. That's fine if we want to load a website, if we want to stream video. It's perfectly okay. It doesn't really hold us back. But if I want to start doing things like, for example, actual streaming of gaming, I want to have fast response to my user input. 130 milliseconds doesn't count it. If I want to do remote control, remote operator of devices, mining equipment, robotics, remote health, I need low latency. Things get really interesting when the latency starts dropping below 20 milliseconds. And so that's really the big innovation play that comes with 5G, is the lower we get that latency, it's going to open up entirely new ways of developing applications and services to customers that we haven't even dreamt of yet. So I'm really excited to see how this goes. Still, nothing beats local wide, less than 3 milliseconds most of the time if you have piece of copper or fiber optic cable directly to it. This is where AWS Outposts really comes in to play. Right? It's pushing the storage and processing capabilities as close to those end users as you possibly can. Hospitals, for example, mine sites, financial institutions where they have incredibly low latency needs, local zones, outposts but not in your on-premises environment. And then wavelength, which is about taking some of the technology from Outposts, for example, and embedding that directly within the telecommunications network for the delivery of 5G applications that will be developed by ISVs all around the world around these new services as they go through. So you might be looking at this and going, what are my next steps? The thing I'd say is, learn and be curious. It's actually one of our 14 leadership principles at Amazon. So I want to share with you some good resources if you want to kind of dive deeper into some of these. The first is the Amazon Builders Library. This is us kind of sharing some of our best practices. There's some really good things here, such as leader election in distributed systems, which is incredibly complex. One of my favorite, I love it when I'm in a meeting and people start talking about shuffle sharding, particularly there's someone who's never heard that term before, and they kind of think, are we joking with them as they go through? But these are deep dive articles, and they go more than just the technology. They talk about culture, the organizational structure, team dynamics, etc., around some of these aspects as you go through. You might have heard me use the phrase a couple of times, are you well architected? This is a great framework. It measures you across 5 different pillars: operational excellence, security, reliability, performance efficiency, and cost optimization. You can run these reviews yourself. It's guided, and it will even have little links to videos that give you best practices on if you do identify something that maybe is not best practice. By the way, sometimes it's okay. If it's a test system, it doesn't need to meet all of the best practices. So it allows you to just be conscious around the decisions that you're making. If you're looking to deploy solutions, aws.amazon.com/solutions. There are over 218 pre-built solutions there that allow you to get started really rapidly. If you want to experiment with what's it like working with a connected vehicle, what type of data is it going to generate? Let me turn the dial up to 11 and see what it's like under load. And I've got thousands and thousands of messages coming in, and can I map that in real time, for example? There's a connected vehicle toolkit in the solutions builder. What if I want to have a virtual and-on cord for when things go wrong in a ticketing system? That exists there. So there's lots and lots of fun services there that you can get started with, and you can extend them, you can modify them, you can do what you like with them. There's some links here to next steps. First thing I'd say is read. Second thing I'd say is get hands-on with tech. There's documentation, there's the architectural side, there's well-architected solutions, quick start programs. There's also the free tier. No better way to get started than being free. And if you really want to kind of prove that you know this knowledge, get an architectural certification. It's highly valuable. When I talk to customers, the number one question they ask me is, Glenn, who can help me do this? And it's so much easier when they can see that there's someone who's already certified, they know this knowledge. With that, thank you very much. Enjoy the rest of reInvent.